section 4.1. There are a couple copies up here. So yesterday we learned about discrete distributions. Today we're going to learn about some uniform ones. Again, there's many more distributions that are famous enough to have names. These are just going to be a few of them. Okay. The first one is the easiest one. It is the uniform distribution. Okay. And it's just a flat probability density function. Okay, so it just makes a nice looking rectangle. And we say that x is distributed uniformly from A to B. Okay. So again, notice the actual PDF is just the flat line. It goes from A to B. So, for example 1, let's again let x be this uniform distribution. We want to find the PDF. Okay. So just using some logic, what do you think this PDF would have to be? Okay, what do you know about PDFs? Okay, it's the function. We know PDFs have to be positive and they have to integrate to 1. So we know the total area under the curve has to be 1. Now where this is a rectangle, can you tell me what the equation of this line would have to be to make that a rectangle with area 1? Okay, so how do you find the area of a rectangle? Okay, can you tell me the width of this rectangle? So we know the area has to be 1. What is the width going to be?
B minus A.
B minus A. And so if you wanted the area to be 1, then your length would have to be, instead of doing length times width, let's do height times width. Okay, so if our width is B over A, then to get this area of 1, my height would have to be 1 over B minus A, right? So the height of that rectangle has to be 1 over B minus A. And with all density curves, the density curve just describes the height at any point. So my PDF is going to be f of x equals 1 over B minus A. So all we have to do is just describe the height. The height is just this flat line that is 1 over B minus A. Okay, once you know the PDF, we can find all these other things like the CDF. How do we go from PDF to CDF? We integrate. Okay, what are my bounds going to be on this integration? Okay, A, if I go from A to B, I'll just get a number out, and I need to have an x in my equation for my CDF. I'm going to integrate from A to x, so we always integrate with our upper bound as x for our CDF. 1 over B minus A. Okay. And we're supposed to have a dummy variable like t. There is no actual variable in my function yet, but I'm still going to put dt. And this will integrate to, let's see, 1 over B minus A times t evaluated from x to A. And it will give me x minus A over B minus A. And that is my CDF. Notice how all of these formulas are dependent on your endpoints. If I wanted to find the expected value, what's our formula for expected value? We have to integrate over the entire region, so from A to B, x times our PDF, which is just 1 over B minus A dx. Let's go ahead and put in our calculators. So we get A plus B over 2. Now, if I thought about that, I could have figured out the expected value without actually doing the integral, because you remember how I showed you that one little thing that said if you have a symmetric distribution, your mean is always going to be the symmetry point. So a line is definitely a symmetric distribution, and the symmetry point would be straight down the middle. So your expected value is just going to be straight down the middle, which is a plus b over 2. And to find the variance, how do we find variance for something? We need to find the expected value of x squared by integrating from a to b x squared times my PDF. So I get that it is a squared plus ab plus b squared divided by 3. And how do I get to my actual variance? If I have the expected value of x and the expected value of x squared, my variance is the expected value of x squared minus the expected value of x all squared, right? So expected value of x squared minus expected value of x squared. And it gives me a minus b squared over 12. Sorry, I don't know why I ran out of room on this page. So we have our PDF, my CDF, my expected value, and my variance. Okay.
Are you solving these on your calculator?
Yes.
You must have an awesome calculator.
I have a TI-89. Anyone else have one of these? Yeah, they make my life easy. Any questions, I guess, on any of these points, like you want me to solve any of these steps by hand, and I can show you? Okay. Remember, I did say on the test that I will give you things that all your integrations and derivatives will just be the power rule, so it shouldn't be too difficult to do if you don't have a TI-89. Any questions on how we did those, though? That's just all the rules that we learned in the last few sections, just applying them.
Could you quickly show us what buttons to push on the TI-89 to enter the equation?
There's some great YouTube videos.
Yeah.
Everything under the sun.
I would say, instead of us doing it here, since not everyone has a TI-89, come to me after class, or go look on YouTube, or I spend a lot of time looking at just the user's guide for the TI-89. But I'll happily show you after class if you want. So for this next example, we have a company that makes hot chocolate mix, has a machine that packages the mixes. The amount in each package varies slightly from the nominal amount. So for example, the 16-ounce containers usually contain between 15.95 and 17 ounces of hot chocolate. And we are told that we can assume that this is uniformly distributed. So when we look at this, okay, I've gone ahead and I've given you the PDF and the CDF just because I wanted you to see what they look like. So if this is uniformly distributed, so we can say like X is uniformly distributed, and what are the two endpoints? 15.95 and 17. So, for example, if I wanted to find my PDF, f of x, I could just use my formula from up above. We know it's just going to be 1 over 17 minus 15.95. .9523. So my PDF is just this straight line at 0.9523. And then what I really wanted to do was show you, well, this is 4x between 15.95 and 17. What is it everywhere else? 0. Okay. If you want to look at the actual CDF, we know the formula for that is x minus a. A is your first endpoint, your 15.95, divided by your b minus a. And so that is my CDF. When you think about this, if you simplify it, what kind of function is that? That is a linear function. We just have our x value. It's a linear function. Specifically, it's this linear function for x values between 15.95 and 17. And what is it going to be everywhere else? So we have our linear function here. Before we got to our first x value, all the probabilities were 0, so my cumulative probability was 0. Once we get to our 17, we don't add on any more probability anymore. We just keep adding 0, and so we say at a flat line at 1. So I just kind of want to show you what the CDF would look like there.
On the bottom of the second part, isn't that not 0.9523 because you divided by 1? Shouldn't it be like 1.05?
Yes, thank you. Okay. So I just looked up here, but I shouldn't have. What is it?
1.05.
1.05. If you actually do 17 minus 15.95, you do get 1.05. Thank you. I thought I saw some weird looks at that point. So I think we got slightly ahead of ourselves because on example 3, I gave you just wrote the problem statement again, and now I'm asking you to find the PDF, which we ended up saying is just 0.9523. And capital F of x is x minus 15.95 over 1.05. So we already found those two things. Now find the mean amount per package. So mean amount means find the expected value. So mu or expected value, whichever notation you feel like using. And what was our formula for that? It's just the average of the two endpoints because we just want our middle point. So the average of the two endpoints. So that would be a plus b over 2. 15.95 plus 17 over 2. $16.475. Now if we want to find the standard deviation, the first step is to find the variance. And our formula for this is a minus b squared over 12. So 15.95 minus 17 squared over 12. .0918. And if I want the standard deviation, how do I get to the standard deviation? Just take the square root of my variance. 0.303. How do you feel about that? And then we have, for an example, find the probability that the machine underfills the 16-ounce container. Now, you could do this using the techniques that we've learned in this class, and we could do integrals or use a CDF. But honestly, with the uniform distribution, I'm going to challenge you to just remember it's a rectangle and pretend you're back in a junior high class and you've never heard about calculus. Okay? And because we know how to find the area under a rectangle, don't we? It's just length times width. So that's how I was thinking about it for the uniform. So I always remember, okay, so I have this rectangle that goes from 15.95 to 17, and my height, what did we say the height is? The height is 0.9523. So if I'm looking to underfill the 16-ounce container, I'm trying to find the probability that X is less than 16 ounces. Okay, so what would that look like on my graph? That's saying, okay, well, here's my 16, and I'm just looking for the area here. Okay. So he said 0.05, the width, and then what? Times it by the height, which is a constant, 0.9523. So 0.0476. Could you have just used the CDF on this problem? So you could have just plugged 16 into the CDF and you would have gotten the same thing. But I think it's kind of fun to just treat it like a rectangle. So just one more example of it. We're just going to go through. So what is the PDF for this next example? So suppose we have the size of a certain type of marble is uniformly distributed with a diameter that's uniformly distributed between 0.3 and 0.5 inches. So X is distributed uniformly from 0.3 to 0.5. So f of x is just, tell me what the height of the line is going to be. So it's 1 over b minus a. So 1 over 0.5 minus 0.3 gives me 1 over 0.2, should give me 5. So it does give me 5. So basically we have this rectangle that goes from 0.3 to 0.5, and the height is 5. What would have happened if you had accidentally switched the order of these 0.3 and the 0.5? You would have gotten the same answer, but it would have been negative, and you should know that your PDF always has to be positive, and that should give you a good clue that you messed up somewhere. Okay, for the CDF, it's just x minus a over b minus a. Okay. So this is x minus 0.3 over my 0.2. What about the mean? We know that the mean is just the average of the two endpoints. What is the average of those two endpoints? Just 0.4. And the variance is b minus a squared over 12. So 0.5 minus 0.3 squared over 12. 0.00333. And to find the standard deviation, I just take the square root. 0.0577. So the next is find the probability that a randomly selected marble is between 0.35 and 0.42 inches. If it's a continuous distribution, do I have to worry about whether I write a less than or equal to or just a less than? Okay. We decided for continuous distributions, it doesn't matter whether you have less than or equal to or less than, because the probability at any single point is 0. So here's my 0.3, here's my 0.5. I am trying to find the area from 0.35 to 0.42. Okay. So what would that be? What is the width of that? My width is 0.7, and my height has to be 5. So this gives me 0.35. For my next one, I'm trying to find the area from 0.2, which would actually be over here, to 0.34. Okay, now when I actually try to shade that, I can shade this area here, but what is the area outside the box? What is the height outside the box? 0. So I'm not going to get any area there, right? So really, where do I start counting my area? At my 0.3. So my width goes from 0.3 to 0.34, so that gives me 0.04. Oh, let's come back up above. What is the actual difference between 0.35 and 0.42? 0.07. So 0.0 is still 0.35. So on this next one, I go from 0.3 to 0.34, which gives me a width of 0.04, and my area has to be 5, so 0.2. And my very last one, I want to go from 0.47 on. It didn't give me a stopping point, which means that I'm trying to go on forever. But my actual area, I can only go from 0.47 to 5, and then I just go on forever this way. But my height outside the rectangle is 0, so my area outside the rectangle is 0. So what is my actual width of the area that I shade? 0.03. My height has to be 5, so my probability is 0.15. Okay. So, questions on the uniform distribution. Okay, just treat it like a rectangle. I think it's kind of fun. Our next distribution that we're going to talk about is not a rectangle. Okay, it is the exponential distribution. The exponential distribution has a parameter, lambda, and lambda has to be greater than 0 for this to work. It's useful for modeling time, so like a waiting time, a failure time, time to death, time to charge a battery, anything like that when you're trying to model the time. The probability density function is defined as f of x equal to lambda times e to the negative lambda x. Do you see why lambda has to be greater than 0? Because if lambda wasn't greater than 0, then we would get a negative PDF, and we have to have a positive PDF. It's only defined for x greater than or equal to 0. So anytime you have an exponential, it has to be for x greater than or equal to 0. And otherwise, f of x will be 0. The cumulative density function has a very nice formula for us. It's just going to be 1 minus e to the negative lambda x, again for x greater than or equal to 0. We have formulas for the expected value and variance. Again, pretty simple looking formulas. Not too bad to plug things in. And just for an example, I wanted you to see what does it look like. So here's the PDF for x distributed exponential with lambda equals 1. Okay, you can see the actual equation for the PDF and the shape. And just so you have something to compare it to, here's an exponential function for lambda equals 0.5. Okay, notice still the same shape, we just pushed it down a bit. And that lambda can be anything greater than 0, so I could do lambda of 1,000, lambda of 50, anything you want, but it's going to maintain this same basic shape. Okay. Why do you think this is useful for modeling waiting times? Because usually you're not going to have to wait very long, so your high probability should be at the top, and eventually as it goes out, your waiting time should get shorter and shorter because you should have to wait less and less. So usually we model it for things where the probability of it happening gets less and less the longer you wait. Now, as a note, the exponential distribution is very interesting because it has what's called the memoryless property. So this means that if you already know that you waited, say, 5 minutes, that doesn't change the probability for or the expected time that you still have left to wait, which seems kind of counterintuitive sometimes. Okay? So we only use it in situations where this would be appropriate. So again, it's where the conditional probability doesn't make a difference. So if I already know I waited this long, that doesn't change how long I have left to wait. Okay. And again, it doesn't make sense all the time. Okay, so for example, a place where it would make sense is if you're trying to model the time until a failure of an electrical component, but it's just due to random fluctuation. Okay? So if it's just the failure is due to random fluctuation, then knowing it's already lasted 10 days isn't going to change the probability of it, say, lasting another 10 days. But if you have something like where you're trying to model it based on just the wear and tear, natural wear and tear, then what's going to happen? The longer you wait, the longer it's been in service, the higher and higher the probability would get that it is going to wear out. So the exponential wouldn't make sense in that case. Okay, so we're not going to have a lot of problems where you have to decide if the exponential makes sense. Just know that it is there. It is a valid distribution if you ever have to use it in the future. But it does have that memoryless property. So we have one example here. So the post-diagnosis survival times in months of victims of a particular type of cancer are given by X, where X is distributed exponentially with lambda equals 1/15. I'm going to ask you, what is the PDF? And all you have to do is plug lambda in. So f of x equals lambda e to the negative lambda x. And so we just plug lambda in. So 1/15 e to the negative 1/15 x. And that is your PDF. And we know that it is for x greater than or equal to 0. And similarly, if I want the CDF, all I have to do is plug lambda in into the equation. So 1 minus e to the negative lambda x. Again, for x greater than or equal to 0. Now, just kind of a review of different things. What if I asked you to find the median survival time? How did we find the median before with our continuous distributions? Do you remember? Okay. So the median isn't the expected value, but okay. So, say it louder. Set equal to 0.5 because the median is finding is the point where half the probability is below and half the probability is above. So if half the probability is below, we can set the CDF equal to 0.5 and solve for x. Okay. So we have 0.5 equals 1 minus e to the negative lambda x, or 1 minus 0.5 equals e to the negative lambda x. So let's see. Negative lambda x equals natural log of 0.5, x equals natural log of 0.5 over negative lambda x. Oh. Natural log of 0.5 over negative lambda. And I guess we know what negative lambda is. Let's see what that gives me. It gives me 10.39. So my median, the middle value, half the probability below, half the probability above, is 10.39. If I didn't make any mistakes in my algebra, feel free to correct me. So this is where it becomes fun, is where I actually find the probabilities. So what is the probability that a patient will live 6 months past the cancer diagnosis? I'm going to put in here, live at least. So the probability that x is greater than or equal to 6. Okay. How could you find this here? You have two methods. Again, we could use the PDF or the CDF. If we use the PDF, we will have to integrate. If we use the CDF, we don't have to integrate. So if I want to use the CDF always tells me the probability that we are less than or equal to. So if I'm greater than or equal to, I need to do 1 minus. Okay. And again, continuous distribution, so it doesn't matter if I have greater than or equal to or just greater than. Okay. So it's 1 minus the CDF evaluated at 6. Okay. So I have my CDF up above, so I just plug it in. So 1 minus e to the negative 1/15 times 6. .6703. So for this type of cancer, there's a 67% chance that you will live at least 6 months after your diagnosis time. Now, if this is an exponential property distribution with the memoryless function, what this means for us is if I already know, say, that I lived 4 months, that doesn't change the probability that I will live another 6 months. The probability that I will live another 6 months is always going to be 67%, no matter how long I've already lived, if it's truly an exponential distribution. So for the next one, the probability that x, they live between 2 and 13 months, so x is between 2 and 13. Okay. Again, I could use the PDF or I could use the CDF. So I'm going to use the CDF just so I don't have to integrate. So it's going to be f evaluated at 13 minus f evaluated at 2. So I plug 13 and 2 into my CDF. Now I need to put them in my calculator. Make sure you put in enough parentheses. So the probability that I will live between 2 and 13 more months is 45%. And so that's 45% at the time of my diagnosis that I'll live between 2 and 13 months. Then if I already know that I've lived, say, 7 months, the probability that I will live another 2 to 13 months would still be 45%. Expected survival time. The formula for that is just 1 over lambda. We have 1 over 15 gives me 15. So we expect to survive another 15 months. And if I want the standard deviation, that's just the square root of the variance. So it's the square root of 1 over lambda squared. So square root of 1 over 1/15 squared is just going to give me 15 again. So 15 months. So, questions about the exponential distribution?
Is the expected value and the standard deviation always going to be the same?
Yes, because, so you'll notice here, the variance is defined as 1 over lambda squared, but if the variance is 1 over lambda squared, then the standard deviation when you take the square root is always just 1 over lambda, which means that the standard deviation and the expected value will always be the same for this exponential distribution, which is kind of interesting. Any other questions? At this point, we're just kind of trying to get you used to and exposed to several different distributions so that in the future if someone says, well, go use the gamma distribution, even though you haven't seen it before, you can go to Wikipedia, you can find the PDF, and you can do everything you need to from there. Okay, just the fact that you're used to working with different distributions. So this is a good time